Hey, before we continue, please consider subscribing to two excellent channels about IT, Avocodus and AveTech. Avocodus is a great channel with programming tutorials and IT humor, and AveTech is about the stories behind tech and business. Links are in the description. Thank you.
So let's use a Caesar cipher with shift of 3 to encrypt the message we write at noon. So the Caesar cipher is also called a basic shift substitution cipher. The idea is that we're going to take the alphabet, A, B, C, D, E, F, so on and so forth, and we're going to shift it several spaces. So in this case, we're going to shift A 3 spaces over, and so A is going to map to D, B is going to map to E, and so on and so forth. So we're going to shift the alphabet over. So the entire shift here would look like this. A would map to D, B to E, C to F, so on and so forth. So to encrypt the message we write at noon, we simply encrypt each character. So W maps to Z, E maps to H, and typically we just do everything in uppercase. R maps to U, I maps to L, D maps to G, E maps to H, A maps to D, T maps to W, N maps to Q, O maps to R, R, Q. And there we are. There is our message encrypted. Now, if we just sent it like this, somebody might be able to guess at what some of these words are based on how long they are. And so it's typical to either just combine all the letters into one big long string, or to chunk them up in some sort of standard chunking. So for example, we might group them by 3 characters at a time, something like this. And there would be our encrypted message. So now we can go the other way now, decrypting the message. This one here, if it was encrypted using a shift cipher of shift 5. So a shift 5 would mean that A would be shifted 1, 2, 3, 4, 5 characters over. So A would map to F. The whole mapping would look like this. So to decrypt, we go the other way. If G is the first character of my encrypted message, then B is the first character of my unencrypted message. Continuing on here, Z would unencrypt to U. D would unencrypt to Y. And we can continue this on. And our final unencrypted message looks like this. Now it looks like what the message was supposed to be was buy 50 shares, and we have an extra character here at the end, and chances are that extra character was added in just to make this original message come out in nice chunks of 3. So thinking about this cipher, how hard is it to break this cipher? So suppose you intercepted a message and you know that the sender is using one of these Caesar shift ciphers, but you don't know what the shift being used is. But the message begins EQZP. How hard would it be to encrypt this message? Well, keep in mind that there's only 25 possible shifts, and so it would not be that hard to literally list out every single possible shift and the encrypted message. Or the decrypted message. And if we look through these, only one of these produces text that looks like it's likely part of actual words. And so it's incredibly easy to do what's called a brute force attack on a Caesar shift cipher. A brute force attack being one where we just try every possibility. So this is not a very secure encryption method. So let's use this substitution mapping to encrypt the message March 12th at 0300 hours. So in this case, what we have is what is a sort of random substitution cipher. In this case, a alphabet alphanumeric one that includes the numerals 0 through 9. And basically, these have been randomly shifted, which creates a much larger set of possible encryptions than the basic shift cipher did. So to go ahead and encrypt here, we do the same thing we did before. We find each character in the original and figure out what it maps to. So M is going to map to 6. A is going to map to 2. R is going to map to S. C maps to Q. H maps to T. 1 maps to Z. 2 maps to N. 0 maps to Y. 3 maps to 1. And 0's mapped to Y. And there is our encrypted message using this cipher. And of course, again, we could chunk it out if we wanted to if we wanted to, add some spacing. So how hard is it to break this cipher? Now, it seems like this should be really, really hard because there are a ton of possible substitution ciphers here. In fact, it's about 10 to the 40th, which is a 1 with 40 zeros afterwards. But it turns out that this particular cipher is actually pretty easy to crack using something called frequency analysis. And that's the idea that in the English language, there are certain letters that show up more often than others. For example, the letter E shows up with a really high frequency in English language. So this chart here on the right shows the frequencies of different letters in Common English. And you'll notice here that E is the most frequent letter used, followed up by A, and or A and T are pretty similar there, and a few others. So in this case, what we have on the the left here is some encrypted text, and the frequencies of different letters were calculated. How often each letter showed up in the text. So what can we deduce from this? Well, since the character S here is showing up with the most frequency, it's really likely that our original mapping mapped the letter E to the letter S, and so that S can be unencrypted as the letter E. Now, it's very likely that these two, W and L, came from A and T. So it's very likely that maybe T maps to W, and A maps to L, though those two could possibly be swapped. Now, we could also look down here and see that certain other characters, like J, X, Z, and Q, don't show up very often. And so it's very likely that these characters here, C, A, D, and J in the encrypted text, correspond to those very unfrequent letters. And if we follow this process and sort of decrypt each letter as we go along, then we can start looking for patterns. There are also certain pairs of letters, like TH, which show up very often in English language, and we could use those, again, to help us break the code, break the substitution mapping. And it turns out to be not too hard to do, as long as you have enough text to find these frequencies from. So now we're going to encrypt the message, "Meet at First and Pine at midnight," using a transposition cipher with rows 8 characters long. Specifically, we're going to be using a tabular transposition cipher. Now, a transposition cipher means that instead of changing what the letters are, like we do with substitution ciphers, we're just going to change the order in which the characters appear. In this case, we're going to use rows and columns and change the way we read them. So what we're going to do is we're going to write out this message 8 characters at a time. So we're going to write meet at first, what are we at? 1, 2, 3, 4, 5, 6, 7, 8. And notice I'm leaving out the spaces. And normally I would do this using all uppercase characters. There we are. So meet at first and pine at midnight. Notice we got a few spaces left here, and so normally we would pad the message, which means make up some random characters. So maybe I'll add a P, X, and an R in here in order to fill it out. So that is our message jotted down. Now to create our encrypted text, we are going to rewrite the message reading down the columns instead of across the columns. So our encrypted message will be MRNIESEGETAH, right? Again, I'm reading down the columns here, so next we're going to have TATTANMPTDIX. And I'm going to have to continue down here. FBDNIINR. And now, it would be really important here to either eliminate all the spaces or reposition the spaces to hide the size of the table used, because in this particular method, this information is the encryption key. That's the information you need to know in order to either encrypt or decrypt the message. Now notice that means that we don't have a lot of encryption keys here, unless if we had a really long message and could change this quite a bit. But there are other versions of this encryption where instead of reading down the columns, we could read up the columns, or we could read diagonally along the columns, or we could read in a little spiral pattern. So there are other versions of this type of encryption that we could do. Okay, so now let's see if we can decrypt a message the same way. So in this case, because we know that this was created using a transposition cipher with 20 characters long, the first thing we need, row is 5 characters long. The first thing we need to know is how many total characters do I have here? And in this case, I have 20 characters, and if each row is 5 characters long, that means I had 4 rows. So now remember, this text came from the column, and so to decrypt this, I'm going to write CEEI down the first column. And remember, I just figured out that there's 4 rows, so I know to do it in groups of 4. So now I'm going to continue this for the rest of the message. And there we go. Now that we have it written out in columns, we can decrypt the message by reading across the rows. So it looks like we've got call me in the morning. And it looks like we got a couple extra letters here, VW, which are probably those padding characters used to fill out the table. So it looks like our encrypted message was call me in the morning. So one way to make a transposition cipher a little more complicated is instead of just reading down the columns, we can pick the columns in a different order. And one neat way to do that is using a keyword. In this case, we're going to use the keyword money. And that keyword tells us 2 things. First, it tells us that we are going to do rows with 5 characters, because there are 5 characters in the word money. The second thing it's going to do is tell us the order in which to read the characters. And so what we're going to do is we're going to look at the word money and say, what is the order that these letters appear in the alphabet? So, A, B, C, D, E. E shows up first. A, B, C, D, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, and then Y is going to show up last there. And so this tells us the order in which we are going to read the columns of our encryption key. So we're going to start out by writing out our message in rows with 5 characters each. So that's buy some milk and eggs. And then we're going to need to pad this with a couple characters. So to write down our encrypted message, again, we're going to use this as the key for which what order to write the columns down in. So this says, first, write down this column, the fourth column in the message. So first I'm going to write SIDP. And then second column was going to be this one, right? Because again, this is telling me the order in which to read them. So next I'm going to write down BMKG. Next I'm going to write down the middle column, YMNS. Next I'm going to write down this column. So that's UEAG. And then last I'm going to write down the last column, OLEK. So again, I write down the columns, I read down the columns, but in the order specified by my keyword. So now let's decrypt a message that was encoded using row and column transposition cipher with this keyword. Now this keyword tells me that there was 6 characters per row, and since there are a total of 24 characters in the message, that tells me that there are going to be 4 rows to fill out here. So I'm going to have, and I'm just going to sort of make a little grid here for my reference. So we have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6 columns and 4 rows in each. Now, remember the keyword tells us the order in which the columns were read. In this case, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, V, to the end. Okay, so it tells us that the columns were recorded or read out in this order, and so that is the same order in which we're going to need to write them down. So the beginning of the message came from the last column, because that would have been the first one to get read. So we'll write down RHAV in that column. So then the next 4 letters are going to go in the next column, T, N, U, S. And then we're going to jump to the middle, this column, the third column here, for the next 4 letters. That's R, E, D, E. And then we're going to go to the first column. Remember, this is the 4th one being read. And so now we're going to jot down A, I, E, R. Jot down the next 4 characters. The next 4 characters are going to be from the 5th column that was read, in which case it's the 2nd column of the original. So that'd be I, K, A, T. And then the last 4 characters will go in the last row. So that's S, O, Q, R. And let's see what we've got. So again, now we just read our message out. So we got air strike. So we got air strike on HEAD head quarters, and then an extra character on the end, which was probably our padding. So airstrike on headquarters is our decrypted message. So one way to make a shift cipher a little more complicated and to fool frequency analysis is to change the shift after each character. So this time we're going to use a basic Caesar shift cipher with 3 as the initial substitution, which means A maps to D. But then we're going to shift the substitution 1 additional place after we encrypt each character. So in our initial encryption, we're going to encrypt straight down. So S is going to encrypt. So our original message is see me. So S is going to map to V. Now we're going to imagine this all being shifted 1 more place over, which means that each character, instead of mapping straight down, is going to map 1 place further over. So now E is going to map to I. And then we shift again, which means the next time we're going to map I to, E. E is going to map to J. So now we're 2 characters in. Now we're going 1 more in. That means we're going to shift 3 spaces. So now instead of mapping directly down 1, 2, 3, m is going to map to s. And then our last e here, let's see here, 1, 2, 3, 4. So that last e is going to get mapped to L. Okay, so notice what's happened here is even though we had 3 e's in the original message, each of them has been mapped to a different character because we increased the amount of shift after each character. So let's compute some moduluses. So this is modular arithmetic. You can really think of modulus as remainder after division. So to find 10 mod 3, you can imagine good old long division and say if I divide 3 into 10, what do I get? Well, let's see here. 3 times 3 is 9. So I end up with 3 remainder. So if I take 10 divided by 3, I get 3 with a remainder of 1, and that remainder is what we call the modulus. And so 10 mod 3 is 1. So what happens if we try to find 15 mod 5? So that means we're dividing 5 into 15, and it goes in evenly, which means the remainder after division is 0. And so 15 mod 5 is 0. 2 to the 7th mod 5, this is actually not too bad to find, because 2 to the 7th is 128. So if we want to find 128 mod 5, we divide 5 into 128. And let's see here, 5 goes in 5 times 25, remainder of 3. So we get 25, remainder 3, so 128 mod 5 is 3. Now notice that we're writing it in sort of the elementary school remainder way here. You're probably also familiar with either writing it as 25 and 3/5 as a fraction, or even 25.6, right, converting it into a decimal. And you can actually take advantage of these other approaches to help you find moduluses using a calculator. So let's take an example. Let's look at that. So suppose I wanted to find 31,345 mod 419. So I wanting to divide this way. Yeah, I don't know what that is. So I'm going to pull up my calculator, and I'm going to say 31,345 divided by 419. And I get 74.890 stuff. So I know that the whole part here is 74, right? And so one thing I could do is I could just multiply 74 times 419 and find my remainder at this point. And in fact, that's not too bad to do. We could say 74 times 419 is 31,006. 31,006, and then subtract to find the modulus. But I'm actually going to show you another way to do it. If we go back and we find our 31,345 divided by 419 here, oops, 419 here, which was, let me try that again. 31,345 divided by 419 is 74.89. So what we really want is the remainder part. So let's go ahead and subtract 74 equals, and that gives me the 0.89. Now this 0.809 is the fractional remainder, right? This is the decimal equivalent to some number out of 419. So to figure out what out of 419, we can just multiply this by 419. That's not right. Let's try this again. We're multiplying by 419, and there we go, 339. And so 339 is the remainder. Again, the idea here is that 339 out of 419, which would be the fractional remainder, was that 0.809 term. And so by multiplying by 419, we were able to figure out this numerator. We were able to figure out the modulus of 339. So we're going to compute 12 to the 5th mod 7, and without any tricks here, this would be kind of difficult because 12 to the 5th is like 248,000 and would be a pretty big number to deal with. But the modular exponentiation rule says 12 to the 5th mod 7 can also be written as 12 mod 7 to the 5th mod 7. In other words, I can first find the modulus of 12, raise it to the 5th, and I'll end up with the same result. Now this is nice because 12 mod 7 is 5. Right? Because 7 goes into 12 one time, leaving a remainder of 5. So 12 mod 7 is 5. And 5 to the 5th, while, not tiny, is definitely a more reasonable sized number than than 12 to the 5th would have been. So now I can divide 7 into my 3125, and let's see, 28, 32, let's see, 4 again, 28, 45, and let's see, 6, 42, remainder 3. And so my remainder is 3, and so 3125 mod 7 is 3, which means this is also 3. Now, let's look at another variation of this called the modular exponent power rule, which says that these three things are equal. We're going to specifically check this one compared to this one, using these values here. So using these values, it would be 3 to the 4th mod 7 to the 5th power mod 7. We're going to compare that to 3 to the 5th mod 7 to the 4th mod 7. The theory behind this is that that even with the modulus, that these things behave like exponent rules do. That you can multiply your exponents together, which means you can change the order, which means you can pull it out like that. And we're just going to verify that this does in fact work in the modulus world. So 3 to the 4th is 81. And 81 mod 7 is 4. Let's see, 4 to the 5th is 1024. And then we find the modulus was 7 there, and we get 2. So let's check over here. So 3 to the 5th is 243. And we're going to find that mod 7 here. So 243 mod 7 is 5. And 5 to the 4th is 625. And 625 mod 7 is 2. And they are, in fact, equal. And I know I skipped a lot of steps there showing the calculations of the modulus, but trust me, if you actually do the divisions and find the remainders, these are the values that you come up with. So let's go through the process of the diffie-Hellman-Merkle Key Exchange. So remember, the really important idea here is that we've got to imagine that there's an eavesdropper in the middle here, listening in to anything that Alice and Bob say to each other. And so what they're going to try to do is establish a shared number that they can use as an encryption key. And they're going to try to come up with that without Eve being able to deduce it. So let's see how that works. So Alice and Bob start out by sharing a generator and a prime. These are shared information, and it's fine, and Eve is going to know what these are. Now, each of them is going to secretly pick a number of their own. So I'm going to have Alice pick 8 and Bob pick 6, but they could pick any number they want, and most importantly, only they know it. So Bob and Eve, neither of them know Alice's number, and neither Alice or Eve knows Bob's number. So each Alice and Bob are now going to compute generator to the n mod p. So in this case, for Alice, it's going to be 3 to the 8th mod 17. So let's go ahead and figure out what that is. So I'm going to calculate 3 to the 8th power. 3 to the 8th power is 6561, and now I'm going to divide that by 17 and get this decimal. I want to take away the whole part, so I'm going to subtract 385 and multiply by 17 to get the remainder, to get the modulus. And so my modulus, or Alice's modulus, is 16. So Alice's number is 16. Now Bob is going to do the same thing with his secret number. So he's going to take generator to the n mod 17. And this one comes out to be 15. So now comes the important part. Alice is going to send her number to Bob, and Bob is going to send his number to Alice. So Eve is going to be able to intercept those. But it's really important, because it's hard to figure out. If I asked you 3 to the n mod 17 is 16, it would be hard for you to find n. The only way to do it is to just try a bunch of values. There's no more efficient way to do that. And mod 17, that's not that hard, but if we had a prime number here instead of 17 that was, say, 100 digits long, it would be practically impossible for you to try out all values. And that is where the security of this method lies, in the difficulty of figuring out these secret numbers from these numbers that are exchanged. So again, Bob, oops, there we are. So Bob just acquired, Alice just acquired Bob's secret number of 15, and Bob just acquired Alice's secret number of, or sorry, not secret number, Alice's exchanging number of 16. I don't know what it's actually called. We'll call it exchanging number, right? So Alice sent her number of 16 to Bob. Bob sent his number of 15 to Alice. So now they each have the other's number. So now each of them are going to take the number that they just received and raise it to the power of their secret number. So remember, Alice's secret number was 8. So she's going to calculate 15 to the 8th mod 17, while Bob is going to take Alice's number, raise it to his secret number of 6, mod 17. And if we do that, let's see what we get. 15 to the 8th is a really big number, divided by 17. Oh, I'm going to have a little hard time doing this by using this calculator. So I actually already computed this using a cool little website which lets me calculate these out. And this value turns out to be 1, and this value also turns out to be 1. And this is based on that modular exponent power rule, which says that these things are going to end up being the same. And what's great is that the eavesdropper Eve has no way of deducing this number from the information that was exchanged. So suppose that Alice has computed RSA public keys of n equals 3127, E equals 3, and then she has her private key, D equals 2011. And the really important idea here of RSA is that if we take any number at all, and raise it to the E times D mod n, that will get our message back out. And so the encryption step is this part here, raising the message to the encryption key, mod 3127, and then the decryption step comes from raising that result to the private key. And again, the security here lies in the difficulty of finding these values, E and D, if all you know is N and E. There's no known way to do that. So let's see what would happen with the message 50. So to encrypt the message, Bob would take the number 50, and he has Alice's public key. So he's going to take 50 to the power of the encryption key and calculate 50 to the third mod 3127. And he's probably going to need a little bit of a calculational help for this, but it turns out that this number is 3047. So then to decrypt, so this is the message that Bob then sends to Alice. So Alice then can decrypt it by raising this 3047 to the power of her decryption key, mod n. And again, she's going to need some calculational help, some technology help here, because this is not something that we can compute by hand or on a basic calculator without some tricks. And this turns out to be 50. Right? And again, the whole idea here is it's based on E and D being picked so that 50 to the third to the 2011 gets you back to the original message. But again, even if somebody has the public keys, there's no easy way for them to find the private key from them.
Please consider subscribing to two excellent channels about IT, Avocodus and AveTech. Avocodus is a great channel with programming tutorials and IT humor, and AveTech is about the stories behind tech and business. Links are in the description. Thank you.